Hey everybody, Mr. Covey here, and this is the definite integrals video. We're going to use a little bit of our calculator, a little bit of no calculator together here. Okay? So first off, when we're talking about a definite integral, we're talking about finding the area under the curve. Okay? Keep in mind that when we say that area under the curve, we really mean the area between the curve and the x-axis. Okay? The way that we've been doing this previously in class is using this limit definition of the definite integral, this limit definition of area under the curve. There's different notation that you will see to indicate that you are finding area under the curve. It actually uses the integral symbol. And if you're like, why would it use the integral symbol? There's a connection that we're going to talk about next week. For now, when you see this is what we were doing last week. This means find the indefinite integral. It means find the antiderivative. If you see the integral symbol with a lower bound and an upper bound, that same symbol means a completely different thing. It means find the area underneath this curve from A to B. Okay. So this is fancy notation here for find the area under the curve of f of x from an x value of A to an x value of B. There's definitely some similarities between this and this. You know, so the delta x becomes a dx. We'll talk all more about that later. Okay. Just so we're clear, there's a lower bound, there's an upper bound. These are x values. In the area under the curve of, this is the function. This is what that delta x changes into. So if we're asked to just like sketch the region whose area is given by this definite integral, if you look at this definite integral, here's the function, 3 square root of x. You can throw that in your calculator if you want. Like this. Whoosh. Vertically stretched square root graph. We're trying to find the area underneath it from 1 to 5. So from an x value of 1 to an x value of 5. We're trying to find the area of this region. From an x value of 1 to an x value of 1, 2, 3. 1, 2, 3. Counting is hard. So this definite integral represents the area of this region. Cool. You can calculate this using our limit definition of the definite integral that we've talked about last class, okay? You can also use your calculator. Your calculator knows how to calculate definite integrals. Grab the good old-fashioned calculator, and I'll show you how to do it. Cool? My calculator may look slightly different than yours, so just roll with me here, but it should look the same. Hit the math button. We're in math class, okay? Makes sense. Go down. You know about n-deriv, that's your calculator finding derivatives. There's also fn int, which is your calculator doing integrals. Does definite integrals for you. My calculator is old school. If your calculator is old school like mine, this is what you type in. The function, 3 square root of x. You put a comma, you put an x, you put a comma, you put the lower bound, you put a comma, you put the upper bound, you put a closed parenthesis. If you have one of the new calculators with the fancier math type, it just looks exactly like this. It like literally looks like that. So you put the 1 in there, and you put the 5 in there, and you put the x in there, and you put a dx. Okay, and the other one, it should be easier. This is the one that's a little messier. Function, comma x, comma lower bound, comma upper bound. You hit enter, it spits out a number. That number is the area of that region. That purple region has an area of 20.36 units squared. Okay? Cool. If we're thinking about finding area underneath the curve, okay, there's a few different ways we can now do it. We can use this integration tool on the calculator. We can use right-hand rectangles or we can use the limit definition, that thing we were talking about yesterday. I want to do each one of these together real quick, okay? First, let's use the integral calculator, or integral tool on the calculator. So the area underneath, oops, sorry. So the area underneath 3x squared, I put a comma x, from 1 to 3. $26. That's the answer. That is the exact area under the curve. Please note that this is exact. Gives us an answer of 26. If I use 8 right-hand rectangles, keep in mind it's an approximation. I'm only using 8 rectangles. If I wanted it to be exact, I'd have to use infinitely many rectangles. So this is going to give us an approximation. We can see how close that approximation is. Okay? I'll write it out here with you guys. Okay, so if we're going to use 8 right-hand rectangles, then I'm going to start on the right, and I'm going to use an x value of 3. Oops, sorry. Having some computer problems, sorry. I'm using an x value of 3. Probably be worth it to stop real quick and say my interval is 2 wide. I'm using 8 rectangles, then each one's going to be a quarter wide. So I'm going to use an x value of 2.75, 2.5, 2.252. 1.75, 1.5, and 1.25. So I'm going to take all those x values, I'm going to plug them into the function. To get my heights of my rectangles. Okay, and each of these rectangles has a width of a quarter, so I'm just going to put the quarter on the outside. Okay. Here are the heights of my 8 rectangles. Here's the width of them all. Again, visually, what am I talking about? I'm talking about making 8 rectangles, each a quarter of a unit wide. So there would be 1, there would be 2. They're right-hand rectangles, that's why I'm working from the right. You can look at the picture and tell it's going to be an overestimate. Toss this all in your calculator, I'll do the same. I'll toss it all in the calculator. I got 29.0625. Makes sense? Why? Well, it's an approximation, so it's not going to be the same as what the calculator told me because the calculator told me the exact answer. And it's going to be a little bit of an over-approximation. We can see our function there. Those blue rectangles are going to be a little bit over. Okay. Last way we can find the area under the curve is we can find the exact area using that limit definition. Okay. You guys want to try that? We'll do one of these. All right. I know it's a little bit of a pain. Okay. So I'm trying to do this definite integral. I'm going to set up my sigma. Remember, it's the limit as the number of rectangles goes to infinity. Here's my b minus a over n. It's the width of each rectangle. I'm also going to plug in b minus a over n here. I got to put the starting value there. So this is the limit summation I'm going to do. Remember how to do this. This is a good thing to practice. You need to be able to do this for the AP exam. Write it all out neat. It's not my specialty, but I work at it. Oops. Plug it into the function. So I'm going to plug 3 times 1 plus 2 over n squared times 2 over n. I'm going to do some simplifying first. I'm going to get 1 plus 4 over n plus 4 over n squared. 3 times that, and I'll write it like this. Still got the signal? Still as n goes to infinity. Sorry, I forgot to put the I in there. I'm sorry. Correction, go back. Check, I just forgot the I. So then the I shows right there. And then when I FOIL it out, these terms have i's, and the last one is I squared. Cool. So all I'm doing here is FOILing this out, distributing this out. Okay? Moving forward here. I'm going to split it up. Check. I'm going to replace the summations of the i's with the formulas. Okay? So what is the sum of 1? 1n. What's the summation of I? Here, I wrote it out so that you don't have to watch me write. Cool. So let's just go through this slowly. Okay, right here. I've separated out the i's and the n's. Remember, you want the i's by themselves so you can use those summation formulas. Okay, so there's a formula for this that you need to know. There's a formula for this that you need to know, and there's the formula for the sum of a constant that you need to know. I'm going to replace those red things with the formulas. Okay, check. Once I've replaced those with the formulas, I no longer have any i's, I only have n's. Don't forget, this is all still a limit as n goes to infinity. And now I'm just in algebra world. I'm going to distribute the 6 over n into all the terms. I'm going to get still a limit as n goes to infinity. As the number of rectangles goes towards infinity, I get this 3 different terms here. And now I'm ready to evaluate this limit based on top heavy, bottom heavy, MAH stuff, okay? The first thing is just 6. That's easy. The second term is 24. It's going to be n squared over 2n squared. Since it's square over squared, I just look at the ratio of the coefficients. 24 over 2 is 12. Last one here, I've got a 24. That's going to have a 2 there, so it's going to be 48 n cubed, and then the other stuff I don't care about, over 6n cubed. 48 over 6 is 8. Again, it's n cubed over n cubed, so I'm just looking at the ratio of the cubed terms of those coefficients. Okay? Gives me my 3 numbers, add them together, I get 26. Okay? I know there's a lot of algebra here and a lot of stuff to mess up, but I hope in general you're feeling okay about that process. Big summary is that gives us exact area using the limit definition. The calculator gives you exact area. The right-hand rectangles gives you an approximate area. Cool. Okay. Moving on. Oops, I guess. Here's another limit definition. I don't think we need to practice this again. Okay, but if you want to practice, But if you want to practice this again, what you could do is use the limit definition, type this into your calculator, and see that you get the same thing. To clarify, in case you're confused, if you're trying to find the area under this on this interval, it means you're trying to find the definite integral of this function from x equals 1 to x equals 2. This is what you could type in your calculator. You could do what we just did with the limit definition of the derivative, of the area under the curve, of the definite integral, and you should get out the same thing as what your calculator gives you out. Cool. What I'd like to focus on now is a couple of interesting things related to definite integrals. So if you could grab your calculator with me, make sure we're in radian mode. Calculator, we always got to, calculus, we always got to be in radian mode. Okay, and I want to type in this definite integral: 0 to 2 pi, area underneath, sine of x. Okay, so function sine of x with x from 0 to 2 pi, and we're going to get a little bit of a weird result here that I want to discuss. We got 0. That seems very weird. Yeah? If you think about this graphically, you're like, well, how is there 0 area? That doesn't make any sense. Let's think about what a sine of x graph looks like. It goes up and down and back up. This is pi, this is 2 pi, this is 1, this is -1. Why would it tell me that the area from 0 to 2 pi is 0? Well, I think you can probably guess what's happening here. It's kind of saying those two parts cancel each other out. And why is it saying they cancel each other out? It's because it counts area below the x-axis as negative. This is very important. Okay? So when you're evaluating a definite integral, area below the x-axis is negative. Okay? That's why we use the idea of area in quotes, because area can't be negative, but definite integrals can be negative. Okay? If I asked you to find the area underneath sine of x from pi to 2 pi, that would be negative. Why? Because it's all underneath the x-axis. Okay? Now, in the case of our original problem, the part above the x-axis and the part below the x-axis were the same size, and so they canceled each other out. Our positive area and our negative area were the same area. Okay? Why does it count negative area, area below the x-axis is negative? One way to think about it is, remember we're finding the area of really infinitely many rectangles? And if you think of drawing one of these rectangles below the x-axis, its height becomes negative. So when you do base times height, the height is negative. So that gives you a negative area. Cool. Okay. Couple things here that are really important. These are rules for when you look at definite integrals. If you understand that we're finding the area under the curve from here to here, these rules make a lot of sense. First one totally makes sense. You're finding the area under the curve from 3 to 3. There's no area. You haven't gone anywhere. Okay. Next one's important. If I ask you to find the area under the curve from 3 to 1, that's weird. It's supposed to go from 1 to 3. Okay, the lower bound is supposed to be the bottom one, and the upper bound is supposed to be the upper one. So if the bounds are flipped, what happens is you're moving backwards, and so that also gives out negative area. Okay, so this equals the opposite of whatever the area is from 1 to 3. I'll skip that over. So if you found the normal area under the curve from 1 to 3, and you evaluate from 3 to 1, it's going to be the opposite of it. That's what this rule is saying. If you reverse the bounds, you get out the opposite area. Okay, so if instead of going from 1 to 3, you go from 3 to 1, it's the opposite of what it was. Okay? This is a weird one. This is an important one to pay attention to. Next. This one is totally obvious. Hey, do you want to find the area from 1 to 7, and you find the area from 1 to 5 and 5 to 7? Just add together 1 to 5 and 5 to 7, and you get 1 to 7. Right? That just makes sense. You can take the region and split it up into two different definite integrals and add them together. Next one. If you got a number out there, you can just pull it out. Cool. Kind of makes sense. You can do that with derivatives too. If you're trying to find the definite integral of two things added together, just find the definite integral of each one individually and then add those together. Okay. I want to show you two other problems related to definite integrals. First one here looks weird, not a bad question. If they tell us the area underneath x cubed from 2 to 4 is 60, and the area underneath x from 2 to 4 is 6, and the area underneath 1, because there's nothing there, from 2 to 4 is 2, then we could totally find the area underneath x cubed plus 2 from 2 to 4. How would you do that? Well, let's split it up. I'd say that's the same as this. I'm going to split it up. This, they tell me, is 60. This, I'm going to pull that 2 out. There's an invisible 1 here now. This, they tell me, has a value of 2. And so overall, this area must have a value of 64. This definite integral must have a value of 64. Okay? I'm not actually looking at a graph and finding area under the curve. I'm just using these properties here and kind of manipulating this based on the given information. Okay? There's one other problem related to definite integrals that I want to talk about. There's a blank page on the next page in your packet. If you could try and sketch this down, please. And I want to do these problems together real quick. So I'll give you a second, pause the video, sketch down this picture. Sorry, it's not in there. It's good if you guys practice a little drawing. Take a minute to do that. All right, cool. So hey, they give us a graph here of f of x, and they're asking us to find some definite integrals, to evaluate some definite integrals. What's unique about this graph is, it's got lines. The area, the regions, are geometric. So we can't, just to go back to clarify, because I want to make sure we're all on the same page here. The reason that you can't find the exact area of this region using geometry is because it's not a shape that you know. It's like a weird shape. It's an irregular shape. That's why we have to learn this calculus for finding the area of that region. If you're finding the area of, if you want to find the area of like that chunk, you don't need fancy calculus. It's a triangle, okay? So the calculus helps us when we have irregular shapes, but these ideas of definite integrals we can apply to a graph like this just using geometry. Ready? How do I find the area underneath f of x from 0 to 1? Well, from 0 to 1, it's talking about this region. The area of that triangle, well, base times height, 1 times 1 is 1, but I gotta do 1/2, so the area is 1/2. Below the x-axis, so it counts as negative area. The area underneath the curve from 1 to 4, well, that's this region. I can use geometry to figure this out. Good old-fashioned geometry. Mr. Wilhelm would be proud. Taught me everything I know. That's a rectangle. 1 times 2 is 2. The yellow chunk is a triangle. 2 times 2 divided by 2 also has an area of 2. Add them together. 2 plus 2 is 4. Okay. Looking at this, what would the area from 0 to 4 be? Well, I could do 2 ideas. First, I could say, wait, I got the area from 0 to 1, and I got the area from 1 to 4. Putting them together, 0 to 1, 1 to 4 is 0 to 4, and I get 3.5. Or you could look at the graph, see that the green region we said area was negative 1/2. The blues we said was 4. Negative 1/2 plus 4 is 3/2. 2 more things I want to do. The definite integral definite integral of f of x from 3 to 3. Let's do this one. From 3 to 3, I mean, that's not going anywhere. There's no area, okay? So don't forget about that property. It makes sense. If you're not moving anywhere, there's no actual area. Just from 3 to 3 is nothing. Last one here. This is a hard one. Pay attention right now. The area underneath f of x from 10 to 6. Okay, there's a couple of weird things going on here. It's talking about this region. Well, first, let's just find the area. It's a triangle. It's got 1, 2, 3, 4 as its base. Its height is 2. 4 times 2 is 8. Divided by 2 is 4. So the region's area is 4. Now there's 2 weird things going on here. What's one weird thing? Well, it's below the x-axis. That would make me think it's negative. What's the other weird thing? The bounds, they're in the wrong order. It's going from big to small. That also makes it negative. So if you want to write out a little bit of work, I might say, wait. If I rearrange the bounds and put them in the right place, then it's going to be the opposite of that. Okay? That's one of our properties. Next, the area actually from 6 to 10 itself is negative because it's below the x-axis. So the value of this is negative, sorry, let me move that out of the way, is negative 4. But then it's also the opposite, and so it ends up becoming positive 4. So I got 2 negatives there. So those 2 negatives cancel each other out. The answer to this problem is 4. Why? It's negative because the bounds are backwards, but it's also negative because it's underneath the x-axis. Those 2 negatives cancel each other out to make positive. That concludes this video on definite integrals. Thanks for watching, guys.